right. So next up, we have Helena, who will talk to us about the contribution of mesopelagic fishes to the biological carbon pump in the Northeast Atlantic. So without further ado, take it away, Helena.
All right, thank you so much, Katie. Thanks everyone for coming to listen, and I'll go ahead and get started. All right, so this work is aiming to put fish in the context of the overall biological carbon pump, and we had an opportunity to do this with a really data-rich case study that I'm going to talk about. So to remind us of what Weilei was sharing, we know that the oceans absorb about a quarter of our carbon dioxide emissions. And so that's the big picture. We know that a lot of this is due to passive sinking particle flux when marine phytoplankton grow, die, and sink into the ocean's interior. But a lesser studied mechanism by which the ocean gets carbon down and stored in the deep sea is through this process of diavertical migration. And in this process, fish come up, zooplankton come up at night to feed, and then as the sun rises, they dive back down into the mesopelagic zone. And how does this move carbon? As some of you may be well familiar with, these fish are consuming organic carbon. They're swimming down into the mesopelagic zone, and they're releasing a lot of that carbon through their respiration of carbon dioxide, their mortality, getting eaten by things that stay down in that deep layer, and through their waste products, their digestion and non-fecal excretion. And we also consider that non-migrating mesopelagic fish can play a role in carbon cycling because some of their diet is coming from vertically migrating zooplankton, and by consuming those zooplankton that may have otherwise swum back up to the sea surface and released their carbon to some extent, they're consuming those prey and then releasing carbon in similar pathways as those migrating mesopelagic fish. And so if we look in the literature on fish carbon flux, considering both these migrators and non-migrators, we see that if we represent it in this purple arrow, compared to the total biological carbon pump, the contribution by fish represented in the red arrow is really variable. So in some studies, fish are found to contribute less than 0.1% to the total biological carbon pump. And in other studies, this estimate ranges as high as 30% of the total biological carbon pump. And so this is a huge range, both across studies and also there's a lot of uncertainty within each of these studies. And so one of the things we wanted to do is examine what are the main causes of this uncertainty, which parameters are contributing most, and how can we better put fish into the context of the biological carbon pump with a really data-rich sampling effort. That opportunity came along in May of 2021 when we had the chance to go out on a 3-ship expedition funded by NASA Exports and also the Hui Woods Hole Oceanographic Institution's Ocean Twilight Zone project. And what we're able to do from the fish carbon flux side of things is collect fish biomass data from 2 different ships using 2 different types of nets, 2 different sizes of nets, rather. And those tows off the coast of Europe are represented in the orange and purple lines here. So we have several different tows that we use to estimate fish biomass. And so on this larger, on the larger net was towed from the Sarmiento, shown in the forefront of this photo, and then the smaller Mach Ness net was towed from one of the other ships, the Cook. And so this Mach Ness net that we used on both ships, just different sizes, is the multiple opening and closing net and environmental sensing system. And this is a perfect tool for these questions of fish carbon transport because the net can capture fish at night that are migrating and separately capture those that are non-migrating to get a sense for the biomass of these different taxa of fish that have different behaviors and contribute differently to carbon cycling. And so if we look at what these nets caught, we see here some taxonomic information about the catch. So on the x-axis are the different tows that we did with the larger of the two nets, and the identifications done with both morphology and genetic identification. And you can see that the majority of the fish are belonging to these three different fish families. The hatchetfish shown in the orange shades, bristlemouth shown in purple, and various different myctophid species shown in green. We also see in comparing these two different nets that we get pretty different biomass estimates depending on which net system we are obtaining those estimates from. Unexpectedly, we found that the larger 10-meter squared mouth opening mock nests actually gave us lower biomass estimates when we standardized that by unit effort, by the volume of water filtered multiplied by the depth interval sampled by each of these nets. So in addition to this, for me, kind of surprising result of the larger net catching less per unit volume filtered, we also see that there's really high variability, even looking at the smaller mock nest shown in purple or the larger mock nest shown in green, where sometimes in the same study site, we're catching almost double as the number of fish as in other tows. And I also want to mention we've done quite a bit of investigation into the potential reasons for this difference in the catch between these two different net sizes. We know that biomass is an important contributor to uncertainty in fish carbon transport. So that was one of the advantages of having these two different net types. And one potential explanation is just that this larger net may, for these species at least, create an even bigger, more detectable disturbance in the water, and therefore we may actually get a lower capture efficiency with the larger net. I also just want to mention the bigger net did catch more fish in absolute terms, just not after we accounted for the larger volume filtered. Another bit of evidence that supports this finding, which again is important because biomass is so important in these fish carbon flux calculations, is that from about 30 to 60 millimeters in length of these fishes shown on the x-axis, the smaller net did seem to be catching more in those size classes after standardizing by sampling effort. And so this again also may indicate that there's a little bit more avoidance by the larger net. Okay, so again, the beauty of this net is that we can collect fish at different depth intervals. And so this is looking at results from the smaller net, which had more individual nets on the same net system. And so we have all these different depth intervals that were sampled. And what we use this for in our carbon flux model is to identify which taxa are migrating and which aren't, and how far are they migrating. So what we see is that these myctophids are migrating from 300 to 500 meters up to near the sea surface, whereas the sternoptichids or the hatchetfish are making a smaller amplitude migration, but they're still contributing to the carbon transport based on the flux boundaries that we're examining. We consider a 200-meter flux boundary in our study and also a 500-meter flux boundary. And so you can see that the bristlemouths in general are staying deeper than 500 meters. And so we only consider their contribution through their consumption of some proportion of their prey being migrating zooplankton. All right, so putting this all together and using data from the same time and place, same sampling effort, but from teams that are working on sinking particle fluxes, passive, in other words, passive flux, and also zooplankton active carbon flux, we see that fish make up a relatively modest component of the overall biological carbon pump, but also that there's a lot of uncertainty in that fish carbon flux estimate. The error bars for the sinking particle flux bars, well, I'll first say these are two different methods of measuring sinking particle flux from sediment traps and from this thorium-234 approach. And a lot of the variation there is actually just because from the start to the end of the cruise a few weeks later, there was a really big difference in how much sinking particle flux was measured. And so this just highlights that sinking particle flux is very seasonal. It can change not only by season, but by week even. And so this is likely, given that we were towards the end of the North Atlantic spring bloom in this May cruise, this is likely a relatively low relative contribution that fish are making to the overall biological carbon pump, because at other times of the year, when passive sinking particle flux is lower, fish would be making a relatively higher contribution. And we don't expect fish and zooplankton flux to be, well, I'll say fish, we don't expect fish carbon flux to be changing quite as drastically as these other fluxes because of their longer lifespans, and as far as we know, relatively consistent diel vertical migration behavior throughout the year. So getting more into this error bar for the fish, this uncertainty in fish carbon flux, we wanted to know which types of parameters are contributing most. These bioenergetic parameters that relate to things like the respiration rates and movement of these fish, or the biomass parameters, that is just how many fish are there. And so what we find is that when you consider the dozens, a few dozen different bioenergetic parameters and allow them to vary within their reasonable range, but you keep the biomass parameters constant, you assume that you know biomass perfectly, you see in this violin plot on the far left, this uncertainty due just to bioenergetic parameter uncertainty. In the middle bar, we then keep bioenergetic parameters constant and allow biomass to vary within the true, uncertainty of the different parameters that help us to calculate biomass. And we see that biomass alone is contributing at least, if not more, uncertainty as all of these bioenergetic parameters combined. So this again just highlights the importance of constraining biomass. And then when we consider both of these uncertainties in this Monte Carlo simulation, we see, of course, an even higher overall uncertainty in fish carbon flux at the study site. So diving into these individual parameters even a little deeper, this is what the sensitivity analysis looks like from these Monte Carlo simulations. And this is a lot of information, so I'll just focus first on one of these subplots. So this plot on the x-axis is a standardized z-score just to get everything into the same unit in comparing across different parameters. And on the y-axis is the carbon flux associated with that individual parameter's value. So this catch parameter is just what is the mean catch at this study site. And as you saw, we obtained a distribution of different catch rates at the study site. And so this is just sampling from that distribution to get a mean. And as catch increases, as you'd expect, carbon flux increases. And the slope of this line that is quite high tells us that this is a pretty influential parameter. Now, this is the other biomass parameter that we consider uncertainty for, and this is the capture efficiency. So going towards the lower end of the x-axis here, if capture efficiency is very low, that means that we only expect that we're catching, say, 10% of the fish that are there in the environment because the rest are avoiding the net. And so then we would multiply that biomass up by 10 times to get the total biomass in that space had we caught all the fish with the net that were in that volume filtered. And so in this case, as Q decreases, carbon flux increases. And you can see again from the slope, this is also a really influential parameter. When we look at other bioenergetic parameters, we see that one of the more influential ones is related to the respiration rate. So this is the intercept of the regression that is fit to respiration rates that are measured for mesopelagic fish in the literature, and we also measured some while we were at sea. And this regression is based on the biomass, the mass of the fish, the temperature, and whether they're migrators or non-migrators. And so this is, also something that empirical measurements can potentially constrain in the future. And then all these different parameters are for non-migrating fish. This one is the Z parameter is the proportion of diet of non-detrital origin. So if we go back to that diagram of how non-migrators contribute, if this diagram is just showing the amount that they're consuming that is coming from vertically migrating zooplankton that are consuming that organic, recently fixed carbon at the sea surface, but there's also potentially a proportion of their diet that's coming from detrital origin, and we don't want to include that in active carbon flux estimates because presumably that carbon would have sunk down there anyway. So, if it came from detritus. So this is a parameter that stable isotope analyses can help us to constrain further. The next thing that we wanted to look at in this study and kind of push this field of fish carbon flux a little bit forward from fish carbon transport into carbon sequestration estimates is to ask how much of this carbon that's getting to 200 or 500 meters is actually getting sequestered from the atmosphere on climate relevant timescales. And we based this piece of the analysis on Dave Siegel et al.'s 2021 paper, where they estimated what proportion, shown in the colors on the bottom scale bar here, what proportion of carbon that is injected at, say, 200 or 500 meters is getting sequestered on a climate relevant time scale of here they choose 100 years. And so what we see at our study site is that around 10 or 20% of carbon is getting sequestered on these longer time scales if it makes it to these depths. Oh, and so that's another piece that we add to the analysis. All right, so one of our findings that matches some previous findings in the literature is that biomass is a really important source of uncertainty, and we know this, and we know that there are challenges related to both net and acoustic base estimates of mesopelagic fish biomass, but this is something we can continue to constrain. The respiration rate and activity rates of these fish at different times of the day are also an important contributor to a bioenergetic uncertainty. For vertical migrators, another parameter that we found was really influential was the proportion of fecal pellets that sink below the chosen flux boundary versus getting remineralized at a shallower depth. What this could look like is either getting remineralized into carbon dioxide at a shallower depth or leaching out as dissolved organic carbon before passing that flux boundary. And then for the non-migrators, again, like we saw earlier, that proportion of diet that's from detrital versus non-detrital origin is pretty important. So in the end, at this study site and at this time, towards the end of the North Atlantic spring bloom, and with this really, really rich cruise effort, we find that fish contribute anywhere from 1.5 to potentially over 20% of total carbon flux by the biological carbon pump at 200 meters. And we see pretty similar relative contributions by fish at 500 meters, but a lower contribution in absolute terms at this deeper depth, as we would expect. When we looked at not just carbon transport, but carbon sequestration using that Siegel et al. 2021 paper, we see that fish transport at 200 meters, of the fish transport at 200 meters, about 3 to 37% is getting sequestered for over 100 years. And so I think with this, it's really important to be sure that we aren't conflating carbon transport with carbon sequestration when we communicate out from our fields into maybe a more public audience or policy audience, because it's often the carbon sequestration that we're that other audiences may be really interested in. And so I think this is a big range, and we're still working to constrain it. And I think also that this kind of sensitivity analyses can be useful for figuring out how we can get the biggest bang for our buck in terms of strategically constraining these parameters using empirical measurements that do the most to further constrain. So I think, yeah, doing kind of strategic work in getting a more precise estimate of fish carbon flux is in the works by some people who are even here on the call listening in. So it's great to see you. And yeah, thanks so much for listening. Thank you to our funders. Thank you to more people than I have time to mention who have made this work possible. And I'm happy to take any questions.
Great, thank you so much, Helena. That was a really great talk. Without further ado, does anyone have any questions for Helena? Oh, Lauren, go ahead.
Hey, Helena. That was a really, really awesome talk, really exciting talk. Being the other fish carbon person in the room. I have a couple questions. I guess I'll just start out with a really simple one. With the boats, so it was really awesome that you guys were able to do like a net comparison. Standardization of biomass estimations is of course like a really major source of uncertainty for us. Um, did they also happen to do acoustics to compare as well, or was that not part of this cruise effort?
Yeah, thanks so much, Lauren. Thanks for coming. And we did have acoustics. There were some issues actually with the system on our ship on the Sarmiento, but the Cook has reliable EK80 data. My understanding from talking quite a bit about this with May Sato at Woods Hole Oceanographic is that there's more uncertainties in translating from that acoustic signal to fish biomass that it wasn't even worth trying to come up with a fish biomass estimate. It just, in her view, it wouldn't have been any more precise than the net base estimates. But yeah, and I'll just mention one of the reasons for that high acoustic uncertainty, as many of you may already know, is that the target strength, I'm not an acoustician, my understanding is that one of the main issues is that the target strength of these fish is difficult to know for different species of fish, but also sizes. So the gas-filled, often assume that as the fish gets bigger, their gas-filled swim bladder would get bigger, and so the backscatter would be stronger from a larger fish. But actually, with some of these myctophids, for example, as they progress through life, their gas-filled swim bladder turns into an oil-filled swim bladder. So you get this counterintuitive relationship between fish size and backscatter or target strength. And so, yeah, anyone who is an acoustician, feel free to jump in. But I think that that's partly why we didn't get a biomass estimate from the acoustics. However, we did use the acoustic data to get to inform other parameters that we wouldn't have had estimates from this cruise, but would rather be relying on literature estimates without it. So one of those was the swimming speed of the fish as they move up and down, verifying what depth the main deep scattering layer is at, and where the migrator is moving to and from throughout a 24-hour period, and how long are they spending at the sea surface versus at depth. And so those are parameters that, instead of having a bigger parameter range from the literature, we were able to constrain a little bit from the acoustic data. So yeah, that's how we used acoustics. Thanks, Lauren, for asking about that.
Yeah, no problem. Yeah, I figured it was probably it was probably, a crapshoot with it, but I was just curious to see if you guys had any major breakthroughs or anything like that. But
Yeah, yeah.
yeah,
Yeah,
it's
all those data are available, like they will be available if they're not already. And so, yeah, hopefully, more can come out of this cruise effort in the future.
yeah, awesome. Thank you so much. We'll love to chat with you more. We can catch up later.
Sounds great. I'd love to.
Great, thanks, Lauren. Any other questions for Helena? No, okay, I have one. Thank you so much. That was really fascinating. And oh my gosh, well done with the sensitivity analysis. That's really needed in this field. So great work. I had a question about seasonality at the site, sample site. So you mentioned it a little bit, and I just wondered if I kind of missed a bit of it, so I wondered if you could elaborate any more on that, if that's something that you're interested in looking at. That's something that we're interested in from a similar cruise in the Southern Ocean. So I wonder if you think you were sampling at the peak time and how you think it'll change throughout the year.
Thanks so much. It's a great question. And partway through writing this manuscript, which I'll also just mention hasn't been submitted yet, and we still have some time to incorporate any feedback. So please feel free to reach out if anyone would like to, offer feedback on this. Partway through the process, seasonality was something I was really interested in too. And I haven't been able to find sediment trap data in the same location that necessarily shows a very different passive carbon flux estimate than at this time of year. There are some other studies, but the ones that I found so far seem to also still be in the spring. And I think that would be really useful to know what is this contribution by fish when passive sinking particle flux is very low. And presumably the fish contribution would be higher then. But ultimately, I think an average annual contribution by fish is probably a little bit more big picture, maybe more what policymakers would be looking for, who are looking to manage these species and managing these trade-offs between carbon flux and other potential value of the species. So I don't have an answer to how this would look at different times of the year, other than that we were sampling near the end of the spring bloom. So the fish contribution is probably relatively high. Probably relatively low at this sampling time. And what else was I going to say about that? Yeah, did I answer your question, Katie?
Yeah, absolutely. And I know it's a challenging question. So yeah, that
Oh, I remembered one other thing I was just going to mention. Yeah, not that it's not really more of an answer than that, but I recently read a paper by Francisco de Mello Verissimo, who's working with Adrian Martin, and they were looking at how carbon flux estimates compare it in different times of the year in different regions, and finding that the seasonality alone can explain some cases as much variability as looking at different times of the year. So sometimes if you're looking at northern versus, northern Atlantic versus maybe Southern Ocean and finding a really big difference in carbon flux, it might actually just be partly because of the season that you're comparing. And so yeah, that's something we kind of mention, is that, this is a snapshot in time, but all of this data and results will be publicly available, so people could always compare to passive flux estimates in the same place but a different time of year. Yeah.
Great. Thank you so much. Does anyone else have any questions for Helena? No? Great. Well, thank you so much. Thank you, Helena, and thank you to Lele, who is our first presenter, excuse me. Helena, if you could pop your email into the chat, just so that everyone has that in case, that would be great. Otherwise, thank you all for attending the February Jetson call. Next month, it will be the more Atlantic time zone hosted by Adrian Martin. So stay tuned. And other than that, I hope everyone has a great evening, morning, day, and we'll see you next time. Great. Thanks so much.
Okay, bye-bye.
Thanks, Catherine.
Thanks, Katie. Bye, everyone.